With p-n junctions, we started off just by looking at p-type and n-type material when we stick those together. P-type material, remember, is made up of holes, positive holes, in other words, the lack of an electron. N-type is negative type, so it's made up of negatively charged electrons. You can grow a crystal that's made up of two of those rather than just one type of semiconductor material, and you stick them together, and what happens is that the electrons move into to replace the holes, or they combine with the holes and they leave holes behind them. So what ends up happening is that you get a static buildup of charge in the middle here. So positive charges on one side, negative charges on the other. Because these negative charges here are between two sets of positive charges, they're going to have to overcome the attraction of those positive charges to get across to the other side, so that's not going to happen. And the same goes for the positive charges here. So you end up with a static band in the middle, which is really the junction, where the p-type and the n-type materials join. They are stuck together, and you've got a build-up of static charge there. So you're not going to get very much electricity happening there because there's no movement of charge. Remember, we need movement of electricity, or movement of charges to create electricity. So it's difficult for those charges to move across the depletion layer. So something that we can do in order to make them move is to bias the diode. And we can do that in one of two ways. We can forward bias the diode or reverse bias the diode. One of them involves pushing the charges together across that junction in the middle, which we call a depletion layer, or pulling those charges even further apart and increasing the size of that depletion layer. If we apply a voltage in forward bias, we've got the positive terminal matching up to the positive charges, the p-type material, and we've got the negative terminal, the smaller one, matching up to the negatively charged material, the n-type material. So what ends up happening is that the p-type, the holes are pushed towards the electrons, and the electrons are pushed towards the holes. So they end up combining with each other, and when they combine, you've got movement of charge and you've got energy being released in the process. So holes are attracted to negative terminal, electrons are attracted to the positive terminal. We get charges moving across that depletion layer that we set up previously, and that causes the diode to conduct. In the second case, we connect the battery basically the other way around, so reverse bias. So instead of pushing the charges across the depletion layer to meet each other, they're actually pulled further apart. So we do that by connecting the negative terminal to the p-type material, so therefore it pulls it away. And then we've got the negative charges being connected to the positive terminal, so that gets pulled in the other direction as well. The greater the size of this voltage that you apply there in reverse bias conditions, the bigger this depletion layer will become, so the more and more that will be pulled apart. There are a few applications of the p-n junction diode, and one of those is LEDs. What happens in an LED is you've got p-type and n-type material with a depletion layer in the middle. It's connected in forward bias. And what happens when you shine a photon, what happens is when the electrons and holes come across the depletion layer, they cause a photon to be emitted. And that's just one of the magical things about semiconductors, is that is something that they do. So normally, in most cases, these electrons and holes will combine and they'll create heat, the component will heat up. But in special cases with LEDs, light emitting diodes, they'll emit light instead. So the energy that is released when electrons and holes combine together is released as light, and that's the light that you see an LED give off, whether it's red or whether it's green or whether it's blue, whatever colour it is. And the colour that LED is, the wavelength that it gives out, is determined by the energy that is given off when the electrons and the holes combine with one another. So that's LEDs. The other application of p-n junctions is really photodiodes, and photodiodes can work in two different ways. The first of those ways is the basis behind solar cells. And what happens is a photon will be shone onto the depletion layer, so it's really the opposite of the LED. Instead of giving off light, it's taking in light. And just as an electron hole pair will produce a photon can produce an electron hole pair. So it produces an electron hole pair in the depletion layer here, and then they go off to combine with electrons and holes respectively, and they release energy in the process. And that energy is really a voltage. It registers as a voltage or a flow of electric current. So this is how solar cells work, because you shine light upon them, upon the depletion layer. That causes an electron hole pair to be produced. You get movement of charge, you get electricity being produced. So we say that is in photovoltaic mode. So all solar cells will operate in photovoltaic mode. So the photo part is light, voltaic, that tells you, that electricity is being produced. The difference between that and photoconductive mode, which is the other mode in which a photodiode can work, is that one is connected to a power supply and one is not. A solar cell can make its own electricity, so it doesn't need a power supply, but the basis of LDRs, light dependent resistors, is photoconductive mode, and that's slightly different. So there's no power supply connected to a solar cell. There's a voltmeter, there's some sort of output device that's connected there to receive the electric current that's produced. But with a reverse bias, if you connect a photodiode in reverse bias, remember you've got a large depletion layer, the charges are being pulled apart. So what happens there is that the photon falls onto that depletion layer, and it will cause electrons and holes to be produced, and they will go off and they will give out energy in the process. So it can be used as a light sensor in that way, because the only time you're going to get a flow of electricity through this diode is when there is light falling upon the depletion layer. So you need reverse bias to set up that large depletion layer so that there isn't conduction going to take place. And this is said to be photoconductive mode. In other words, it only conducts when it's subjected to light. So photo for light, conductive for electricity. So conduction of electricity or movement of charges due to the light that is shone upon it, and that's how light dependent resistors work. So you need to be able to identify where both of those are taking place. So that goes back to being able to pick out forward bias from reverse bias.